Hi everyone, welcome to this video, and we'll be discussing the voltage and currents in phasor domain as well as instantaneous domain and their power calculation. So let's dive into question number one. Let's read it together. A generator is producing a 240 volt AC voltage at 50 Hertz. The generator is connected to a load drawing 10 amps. In this setup, the load current leads the voltage by 30 degrees. Provide equations for the instantaneous values of both voltage and current as functions of time. Additionally, sketch the phasor relationship. So the first thing that actually I would like to point out in these type of questions, when there is no reference to whether the values of the voltage or current that are mentioned are whether the amplitude or the RMS value or peak to peak values, in these cases, we would assume that these values are RMS values. In that sense, the voltage RMS of this design is going to be 240 volts, and current RMS is going to be 10 amps. Now let's proceed with calculating the voltage in AC format. So when they are talking about RMS value as 240, the peak value of the voltage is going to be 240 multiplied by square root of 2. So which can be simplified to be 340 roughly volts. And current in an AC format has a peak value of 10 square root of 2, which again equals around 14.14 amps. Now, if you want to actually phasor the voltage and current, in that sense, V in phasor domain can be represented as V peak with the angle of voltage. In this case, since this shows that the current leads the voltage by 30 degrees, we can base our calculation on the voltage such that it wouldn't have any phase. In this case, we can assume that the phase of the voltage is going to be 0 degrees. And with respect to that, I phasor is going to have 30 degrees more than the voltage. So our assumption is going to start from the value of 0 for V, and in that case, the current is going to lead by 30 degrees, which means that we are going to add 30 degrees to that. So in that sense, we can write the instantaneous forms as follows as well. For the voltage, we know that with respect to the time, we have V peak sine omega t. And we know that omega is simply 2 pi f. And since the question is saying that the frequency is 50 hertz, that's exactly this frequency that we're referring to. So in that sense, we have 2 pi times 50, or simply 100 pi. So omega is given as follows. Now, let's simplify this. V peak, we just calculated V peak. V peak is given here as 340 volts, and also the phasor doesn't have any angle, which means that this form of sine wave is enough for us. We just need to add 340 volts at the very beginning. So we would be 340 sine of omega, which is 100 pi t. So that's the instantaneous voltage. Now, if you want to find the instantaneous current, in that case, it would be again I peak sine omega t, but this time we are going to add phase to that as well. So we would add phase of phi to that, and we know that phi in this case is going to be 30 degrees because current is going to lead the voltage by 30 degrees. So in this case, phi is going to represent 30 degrees in radians, which is going to be pi over 6. So it can be simply written as I peak that we're replacing that with the peak value as 14.14 sine of omega t, which again is going to be 100 pi t, plus phi, which in this case is going to be p over 6. We just write it in its corresponding color, p over 6. Now, this is instantaneous waveform for both voltage and current. And also, the next part of the question is saying, additionally, sketch the phasor relationship, the phase relationship. So in order to do that, we know that the angle for voltage is going to be 0. So typically, it's going to be plotted on the horizontal axis because that's the baseline that we are going to plot. So that's the V. And now we know that current has 30 degrees of phase with respect to that. So we can plot current in this direction, knowing that this angle between them is going to be 30 degrees. So that's how you would plot the phasor format of voltage and current with respect to each other. So second question is asking, calculate the time at which the current is at its maximum value in the previous example. So let's talk about the instantaneous waveform of the current. This is the instantaneous waveform that we can borrow from the previous example. And the question is saying, find out at what point of time this sine wave becomes maximum. And we know that the sine wave becomes maximum at 1, which means that the maximum of it becomes 1 at certain points of time. Specifically, the first instance is when the argument of the sine becomes pi over 2. So let's calculate that. Let's equate the argument of that to pi over 2, because when sine of a function is going to be maximum, which is +1, it happens at or sine x, x then becomes k pi plus pi over 2. 2k pi, indeed, if you want to actually know exactly at +1. So it is pi over 2 plus 2 pi angles, or multiple 2 pi angles. So the easiest one and the earliest moment is pi over 2. So in that case, the argument is 100 pi t plus pi over 6 becomes pi over 2. Then we can solve for t as follows: 100 pi t equals pi over 2 minus pi over 6, which essentially is pi over 3. Now, if we divide both sides by 100 pi, we would get pi over 3 times 100 pi, and essentially that reduces down to, we can easily cancel pi's. It would be 1 over 300, which is going to be around 3.3 milliseconds. So that's the position in time where the current becomes maximum. So the third part of the question is asking, calculate the instantaneous current at time t equals 2 seconds. So the instantaneous current is something that we already have found in the previous part of the question as follows. If you want to calculate its value at a certain point of time, we just need to equate t inside argument with certain values. In this case, t is going to be 2 seconds, which means that it then would become 14.14 sine of 100 p times 2 plus pi over 6. So we just need to simplify this value to find out I at the location of t seconds in time. Which, if you simplify that, you would get to roughly the value as follows. So sine of 100 times pi times 2, it would be 100 times of 2 pi, which is going to be nullified inside the sign. So we're left actually with only pi over 6. So sine of pi over 6 is going to be multiplied 14.14. Sine of pi over 6 is going to be 1 over 2. And we're going to multiply that by about 14, which takes us to around 7 amps. So let's dive into the last part of the question, which is asking the instantaneous power equations as a function of time and calculation of the average power. So we will show with two methods how to calculate the average power, one with the instantaneous power and another one with the phasor format of the voltage and the current. However, let's start with the instantaneous form. We know that the current and voltage are calculated as follows with respect to the previous example. Now, if you want to know the instantaneous power, which is a function of time, we just simply multiply V as a function of time to I as a function of time. Now, in order to calculate, so simply this is how the power in instantaneous format will be calculated. It's essentially 10 square root of 2, which is 14, sine 100 pi t plus pi over 6, and times 240 square root of 2 sine 100 pi t. So that is how the pt is going to be calculated. Now, in order to calculate the average value, what we can do is P average is going to be the integration of PT across a period divided by that period. So essentially, that is going to give us the average value of any time domain signal. In order to do that, we just need to consider the 1 over t, which is the period, times this multiplication, which is going to be 10 times square root of 2 times 240 times square root of 2, and then we'll have sine of, I'm going to write it simply as omega t plus pi over 6 and times sine of omega t. So this is going to be calculated in terms of the integration from 0 to t. Now, we know that these numbers are going to be constant and they can come out of this integration. So simply, we can take them out. Square root of 2's are going to be multiplied by each other, and it will be 2 times 10 times 240, and that will be divided by t. Integration of multiplication of two signs, we would simplify this sign as follows. So that can be simplified as expanded into sine omega t cos pi over 6 plus cos omega t sine pi over 6. So that will be how this term is going to be expanded, and all of that is going to be multiplied by sine omega t dt. The integration is from 0 to t. Now, if we expand this with multiplying sine omega t to each one of these terms, we get the following expansions. Sine omega t is going to be constant, so it's going to be squared cos pi over 6 plus, in the second term, we will have sine omega t cos omega t times sine pi over 6. And in each one of them, we'll have the integration from 0 to t dt. We'll keep this constant at the very beginning divided by t. Now you can see that instead of writing sine squared, we can simply rewrite that as 1 plus cos 2 omega t divided by 2. And this cos pi over 6 is going to be kept as follows. We will then calculate the integration across this plus. In the second form, sine omega and cos omega is a multiplication that can be simplified with sine 2 omega as follows. So it'll be sine 2 omega t divided by 2 multiplied by sine pi over 6. And again, the integration from 0 to t dt. So we'll keep this multiplication 2 to 10 times 240 divided by t at the very beginning as well. So let's calculate these integrations. As you can see here, the integrations are from 0 to t across a multiplication of sine and cos functions. But then if we get closer in terms of the integrations, these sine terms are going to turn into a cos term and vice versa as a result of integration. And when they are being calculated from 0 to t, they end up the same value, and eventually they turn out to be 0 over the whole integration. In that sense, we can simplify the right term into going to 0, and also the cos 2 omega from the left term is also going to 0. What will be left essentially is going to be 1 over 2 times cos pi over 6 from the left component, and there will be nothing from the right component. Let's then simplify that further, so it will be cos pi over 6 1 over 2, the integration over dt, which is from 0 t, and then plus 0, which essentially goes back to the right contribution, which has 0, and then multiplied by the initial contributor of 210 and 240 divided by t. So essentially, since this integration goes to t, we can simplify that as t as well, and further simplification becomes t over 2 cos pi over 6 times 2 times 10 times 240 divided by t. And as you can see here, again, we can simplify t and these 2's. So what is left for us is only 10 times 240 times cos pi over 6. I just try to keep these values the same as they are, because we're going to actually compare them with another method. But then eventually we could finally find the average power from this whole system. And you can see that how much of work is required in terms of multiplication of sines and integration over them. And we need to know all the relationships between the sine squared and cos squared. However, there is a much easier way to get that average power as well, and that's what we are going to discuss next. So eventually, we know that P average is essentially VRMS times IRMS with conjugate value. The conjugate value of a complex number essentially is, if we are dealing with a plus jb, its conjugate will be a minus jb. So that's how the conjugate is being defined. However, in terms of the phase, if a complex number such as c with the phase of theta is going to be conjugate, then the amplitude is not going to be changed. However, the phase is going to be negative. In this sense, we can write down VRMS as the value with an angle of theta v times IRMS as the absolute value with an angle of theta I. However, we need to consider that theta I was going to be referring to only IRMS, but since we're considering the conjugate of that, we have to set a negative value for that. So the negative I theta, negative theta I. And so if you simplify this, we have VRMS, absolute value, IRMS, absolute value. And in terms of the phase, those phases are going to be superimposed. In this case, theta V is going to be minus theta I in this case. Since we are dealing with positive theta V, we have the positive theta V here, and a negative theta I, we have negative theta I. Therefore, we remember that VRMS was 240 and IRMS was 10, and the angle difference was 30 degrees. Or in other words, the angle difference was pi over 6. We can write it both ways. Now, we need to consider that this is the apparent power, and in order to get the real power out of that, we need to multiply. So it would be better to start writing that as S. So P average is essentially S times cos theta, which this theta is the angle between the voltage and the current, or the power factor. And in our case, this theta is going to be pi over 6. And it doesn't really matter whether we put it a plus p over 6 or a minus p over 6. Essentially, it's all going to be cos of that value. So 240 times 10 times cos of the angle between them is going to be pi over 6, is going to be our answer for the p average. As you can see here, how easy it is compared to the arduous method we used before, and we finally got to the same answer of the average power. So here is ultimately the exercise that I've designed for you guys, and you can think over the question and try to solve it on your own. If you have got any questions, please leave a comment under the video, and like and subscribe to this channel if you want to see more videos in the upcoming days. Have a good one.